So my first task is really to start to try and build some planets, moons and stars. So here we go, some of the planets and other objects that we have in our solar system. Now I must stress these aren't to scale, but something they all have in common is around any of these objects there's what we call this gravitational field, and it's a region where other objects experience a force. I'd like to consider the Earth first of all, and effectively we can think of the Earth as just this very large mass, which I've just got a mass down here, and basically anywhere around this, in this region we have what we call this gravitational field. Now a field is just a region where an object experiences a force, and in the case of a gravitational field, which we give the symbol G to, the gravitational field is just equal to the force per unit mass. Now when you come to look at electric fields, this might be the force per unit charge, and so on. And because it's a force per unit mass, it has the symbols of newtons per kilogram. So that's the symbol for this field. Now it might also be that you're used to looking at G in terms of the acceleration due to gravity, and this has the same dimensions basically as meters per second squared. So either of these units can be used, but in terms of gravitational fields I'm going to use this one here from now on to make it very clear. And effectively, let's just take away the Earth at the moment. Around this mass, if you put an object up here, it's going to feel a force of attraction down towards the mass. And what we can do to actually show these field lines is to draw them on using a ruler. Now when I've drawn these field lines, I've used a ruler to make sure they're nice and straight. The second thing is I've drawn 8 of them, and all of these field lines also need an arrow to show the direction of that field, because the gravitational field is a vector quantity, which means it doesn't just have size, it also has direction. So I've also drawn the arrows on to show the field. And basically what we have here is what we call a radial field that kind of radiates out from this. And you've got to remember, although it's only a 2D piece of paper, in reality these field lines come up and in all different directions as well, because it's actually a 3D field. Now these field lines all come onto the surface of this object here, but what we can do is often we can treat objects which are like this as a point mass, and effectively what we can consider is effectively all of the mass acts from the central point of this, and therefore we can think of maybe a point mass, and this is where all the field lines point to. If we have something a bit bigger, then all of the field lines point onto the surface. And if we maybe consider something like our Earth, for example, this is what the field lines look like around it. The field lines get a lot closer together, the closer towards the surface, and this is where we have a stronger gravitational field. As we move away from the Earth, the field lines get further and further apart. But what I'd like to consider now is what would happen if we were to keep zooming in and zooming in onto the field lines on the surface of the Earth. As we keep zooming in and we get down towards the surface of the Earth, what we see is that these field lines that come in are all uniform, which means they're equally spaced out and all pointing in the same direction. And it's this uniform field that you're used to walking around in, okay? You know that when you move around the house, the strength of the gravitational field upstairs is the same as it is downstairs. And also, as you move from place to place around the world, it tends to be the same. And in the case of the Earth, the gravitational field strength G is equal to 9.81 newtons per kilogram, and it doesn't really change a huge amount. So basically you need to start to understand gravitational fields as we move on to the next part, where we start to look at Newton's law of gravitation.